In this video, we're going to look once again at modeling a system in 2 dimensions. So what we have here are two masses which are connected by a rope, and the rope is moving over a pulley. Mass A is 82 kilograms and mass B is 23 kilograms. Mass A slides along a surface with a coefficient of friction of 0.20. Mass B accelerates the system by falling downward. Find the acceleration of the system. So let's write what we are given. So the mass of A is 82 kilograms. We have the mass of B as 23 kilograms. And we're told that there is a coefficient of friction of 0.20. Now, we're assuming in this case this is going to be a coefficient of kinetic friction. We're going to assume once this system is released from rest that the objects are moving immediately. So it wouldn't be static friction in this case. We're writing this then and assuming that these objects are going to be moving right away. So this is a coefficient of kinetic friction, and its value is 0.20. So looking at these, the next step would then be to write the free body diagrams for each individual object. We're asked to find the acceleration of the system, and we're also not told the tension in the rope. The other forces acting on the object we can figure out from the masses, but these two values we're not sure of. We're not told what these two values actually are. So I'm going to create a free body diagram for each object. So I'll start with object A. So I'll represent object A with a dot. This is object A. So we know that we have friction, so I'll go ahead and write that first. So we're going to have some friction force, and it's going to oppose the direction of motion. So object A, as soon as this is released, it's going to move to the right because it has some tension force from this rope that's pulling on it. So the resisting of that tension force is going to pull to the left, and that's going to be the friction force. And this is going to be kinetic friction because the box is going to be moving. So this is going to be the force of kinetic friction. And that's related to the coefficient of kinetic friction. And like I mentioned, we're going to have a tension force, and it's going to be pulling to the right. And that's going to be due to the string or rope that's connected to object A. So the tension force is going to pull to the right. And then we know that because this is on Earth, obviously it has a weight force. So we'll have the weight force of object A. And we also know that we'll have a normal force that is balancing out and countering that weight force. So we'll have this normal force that is pointing upward. And what can we say about the weight force of object A? We already know its mass. So this is going to be, the weight force is going to be equal to the mass of object A times gravity. And that's everything then for this first object, for object A. We've got the friction force. We see here that the tension force is larger than the friction force, so it's going to have a net force to the right. So it's going to accelerate to the right. So I can go ahead and write an acceleration vector in here. And we know that the vertical forces are going to balance out. The weight force is going to balance out the normal force. So that's everything for object A. That's all the forces that are acting on it. And now I'm going to create the free body diagram for object B. So it's suspended in midair on Earth, and therefore the force of gravity is going to be acting on it. And we know that object B is going to be moving downwards. So the force of gravity, the weight force, has to be larger than the tension force, which is pulling upward. So the weight force is pointing straight down, and it's going to be larger than the upward tension force. So this is the weight force on object B, and I'm going to make the tension force equal in magnitude to the tension force on object A, because it's the same tension force in the entire rope. It's just pointing in a different direction. So the tension force for object B is going to be pointing upward. So I'm going to make this the same length as the tension force in object A. So this is the tension force, and the weight force is larger, so it's going to move. It's going to accelerate downwards towards the Earth. We're going to have an acceleration vector that's going to be the same as the magnitude of this rightward acceleration vector. Now it's just pointing down to the Earth. And we can also say that the weight of B is the mass of B times gravity. And that's it. So those are the two free body diagrams. We see that the tension force in object A is larger than the force of gravity, so it's going to accelerate to the right. And it's equal to the tension force in object B, but the tension force in object B is less than the weight force in object B, and therefore the weight force is going to cause it to accelerate downward. So those are our two free body diagrams. And now I can start writing the individual force acceleration equations for each individual object. And so we're going to have two equations for object A, because it's working in the vertical and the horizontal directions. And then we're going to have one force acceleration equation for object B, because it's only working in the vertical direction. So I'll start with object A. So this is object A equations. And let's see, I'll start first with the horizontal direction. So in the horizontal direction, we have tension force and the force of kinetic friction. And we're going to follow the conventional signs for vertical and horizontal coordinate systems. So I can draw that over here just to make sure that it's explicit. But rightward is going to be positive x, and upward is going to be positive y. So that's going to help me determine the signs on my individual forces and on the acceleration. So we see tension is positive, so we have a positive tension force since it's pointing to the right. And from that, we're going to subtract because we have a negative friction force. So this is going to be force of kinetic friction. And we know that the general equation is, of course, the sum of the forces is equal to the mass times acceleration. So here we have the sum of the forces. We have the tension force and we have the friction force. And this is going to be equal to the mass of the object. So that's the mass of object A times the acceleration on object A, and we've called that little a. And that little a is going to be the acceleration of the system. So next we know that tension is the common force in both objects. So I'm going to solve this for tension. So I'm going to add the force of kinetic friction to both sides. So we have the force of kinetic friction added to both sides. And this becomes then the tension force is equal to the mass of A times the acceleration of the system plus the force of kinetic friction. And now what is the force of kinetic friction? We have to think back. What is our formula for the force of kinetic friction? And the formula is the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So we have to then think, well, what is the normal force equal to? So the normal force on this object A, the normal force is equal and opposite to the weight force. So they have the same magnitudes. So the normal force is going to be equal to the mass of object A times the acceleration due to gravity. So I'm going to write this in one step at a time. So this equation then becomes, we have tension equal to the mass of object A times the acceleration of the system plus the coefficient of kinetic friction times the normal force. and then substituting in the value for the normal force now. And in this case, we only care about the magnitude. So it's the mass of A times gravity. So this then becomes, continuing down here, the tension force is equal to the mass of object A times the acceleration of the system plus the coefficient of kinetic friction. And now instead of the normal force, I'm writing the magnitude of the weight force. So this is the mass of object A times gravity. And now I'm going to do the vertical directions. So we see here for object A that if we look at the sum of the forces, we'll notice that these are equal and opposite forces here. So for object A, we have the sum of the forces in the y direction are actually equal to 0 because these forces are equal and opposite directions. So if I plug in then my two forces, I can see, and this is what we actually figured out in this previous step, I see that the normal force minus the weight force of object A is equal to 0. This is the sum of the two forces. I have a positive normal force and I'm adding to it a negative weight force. And from this then, if we add the weight force of A to both sides, we see that indeed the normal force is equal to the weight force of object A, which is good. This is what we utilized here when we substituted in this value right here. This is the weight force of object A. So this is equal to the weight force of object A. It's just the mass of A times gravity. That is the weight force. So the normal force is equal to the weight force, and we plug that in here to our equation. So these are our two equations for object A. We have our equation right here. This is the horizontal direction. And then we have the other equation, which is the vertical direction. Okay, now I'm going to look at the equations for object B. So if I draw a little line here, now we're just going to separate this, and we're going to look at the equations for object B. So this is object B equation. And what do we have? Well, we're only interested in the vertical direction, so this is going to be the sum of the forces in the y direction are equal to the mass times acceleration. Okay, so what forces do we have? Well, we have a positive tension force. So we have a positive tension force minus this downward force, which is the weight force, and that is the mass of object B times gravity. And that's equal to, now we need a mass, and we're dealing with the mass of object B, and we need an acceleration. And we have to look here now, this acceleration in the y direction is downward, it is negative. So we need to multiply this by the negative of A. And we don't have a horizontal component, any horizontal forces here, so that's my only equation. So I'll do like I did in the first case, and I'm now going to solve this for t. So this becomes, if I add the mass of B times gravity on both sides, then this equation becomes the tension force is equal to the mass of object B times gravity. That's what I'm adding to both sides. And I'm going to pull this negative sign out front, and then we have a minus the mass of object B times the acceleration. And that's my final equation then for the second object. And at this point, we now have two equations where we see here, okay, we don't know the tension force, so that's one unknown that's shared in both equations. We also don't know the acceleration, and that's also shared in both equations. But since they're both equal to the tension force, then these two equations are equal to one another. So I can eliminate the tension force and set the right-hand side of both equations equal to one another. And then we'll only have one unknown, which is the acceleration of the system. So I'm now going to set both sides of these equations, the right-hand side, equal to each other. And I'll do that over here. So the right-hand side of this equation is the mass of object A times the acceleration of the system plus the coefficient of kinetic friction times the mass of object A times the acceleration due to gravity. So that's the right-hand side of this equation. And I'm going to set it equal to the right-hand side of this second equation, which is the mass of object B times gravity minus the mass of object B times the acceleration of the system. And now I want to get my acceleration of the system on both sides here. I want to be sure they're on the same side of the equation, and I'll do the same then with these two terms that have the acceleration due to gravity, because I want to be able to get A by itself. So I'm trying to get little a by itself. So I'll pull this down here, and what I'm going to do is I'm going to subtract the second term, mu sub k times the mass of A times g. I'm going to subtract that from both sides. So this is going to get subtracted from both sides. And then I'm going to add this term, this negative mass of object B times A, and I'm going to add that to both sides. So I'm going to add mass of object B times A on both sides, adding the mass of object B times A, and then I'm going to combine everything. So I have a positive of this value and a negative, so that is 0. And then I have a positive of this value and a negative, so that is 0. And then I combine everything else on either side of the equation. So I'll do that down here. So the left-hand side becomes the mass of object A times the acceleration of the system plus the mass of object B times the acceleration of the system is equal to, we have the mass of object B times gravity minus mu sub k times the mass of object A times gravity. And then I'm going to factor out the little a and little g from both sides. So a then factored out is times the quantity, the mass of object A, plus the mass of object B, and g is multiplied by the quantity m sub b minus mu sub k times the mass of object A. And then I can divide both sides by the quantity, the mass of A plus the mass of B, to get A by itself. So I'll do that on both sides of the equation. And this then becomes, we have A is now by itself because these two values are the same number divided by themselves, so that is 1. So we have A equal to little g times the mass of object B minus the coefficient of kinetic friction times the mass of object A over the mass of object A plus the mass of object B. And after all that work, we're now ready to plug in the numeric values here. We have all of these. We have the masses, we have the coefficient of kinetic friction, we know what the acceleration due to gravity is. So I will move this up a little bit and we'll go ahead and finish this problem and get the numeric values. So I'm going to just be plugging in the masses and the coefficient of kinetic friction. So we have the acceleration of the system now is equal to, we have little g, so that's 9.81 meters per second squared. That's multiplied by, we have the mass of B, so that is 23 kilograms, minus, we have the coefficient of kinetic friction, 0.20, which is multiplied by the mass of A, which is 82 kilograms. So both of those are in the parentheses. And then we have the mass of A, which is 82 kilograms, plus the mass of B, which is 23 kilograms. So we have all these numbers here, and I'm just going to put all of these in my calculator. For a number like this, with all these parentheses, you have to be careful and just be sure that you're including all the parentheses so you don't have any issues with the order of operations. So I'm going to enter 9.81 times, open parentheses, it's going to be 23 minus 0.2 times 82, and then I'm going to close parentheses, and then put a division symbol, and then open parentheses again, and put 82 plus 23, and I'm going to close the parentheses. And this gets me a value now for the acceleration of the system, and it is rounded to 2 decimal places. It's 0.62 meters per second squared, and that is equal to the acceleration of the system. So when we look at this, we can see that this is much slower acceleration than if the box was just allowed to fall under the effect of free fall. It's much less than 9.81 meters per second squared. So the friction of this surface above here is really causing this to slow down quite a bit. We have both the friction of the surface and also the resistance of this larger mass A, which is preventing the system from accelerating to a great degree, much less than just if it were allowed to free fall under the effects of the acceleration of gravity alone. So what we did is we created free body diagrams for both objects, and then we solved for the different equation of motions for both objects. So one object had forces in 2 dimensions, and the second object only had forces in 1 dimension. And then we combine those equations using the common factor of the force of tension, which was common throughout the system. And from there, we can solve for the individual components that we're looking for, such as the acceleration of the system.